So last week, you have studied some computational graphs. And this week, we are going to do more depths about computational graph. And you know that for linear regression, we can draw a computational graph like this, where we first multiply the weight as the input and then add it with the bias. So that is a graphic representation of linear regression. And we can use computational graph to represent more complex predictors. For example, in here, we show a classification a machine learning model where we still have a linear unit over here. So that is the same as linear regression. But here we use a hinge loss. But here we use a hinge loss. So this is a loss function in SVM, that is support vector machines. And in addition to a different loss function, this is basically the metric, right? So we are trying to minimize the hinge loss in this model. And there's also a regularization, right? So this is a regularization term added to your loss function. So this is a model with a hinge loss, like in SVM, and also a regularization. So it's a regularized model. So use this computational graph. We can represent complicated models in a simplified graphic representation. Let us look at a multi-layer perceptron, which is a neural network with a hidden layer over here. So this is the input unit. And there are 6 neurons, 1, 2, 3, 4, 5, 6. So there's 4 hidden neurons and 2 output neurons. And this is the sigmoid. So this is the same sigmoid as we learned in logistic regression for the hidden layer. And this is the sigmoid function for the output layer. And we can see the weights are W1 and W2, and the activation functions are our sigmoid, and you notice there are also 2 bias terms over here. So here's a question. How many model parameters are there for this perceptron, multi-layer perceptron here? So I encourage you to pause the video and do some calculation before you see the answer. So please pause your video and compute the answer, and then I will explain. Right? So here is the answer. We look at these 2 weight matrices. The first weight matrices basically is a linear combination of the input with the 3 units to 4 units, right? So we need 4 weights for each of these 3 units, right? So therefore, we need 3 times 4 parameters for the weights over here. And then we look at the second weight matrix, which is W2. And we have 4 neurons over here, and there's 2. So for each of these 4, we need 2 weights, right? So we have 4 times 2 weights. In total, we need 20 weights for the weight matrices. And in addition to that, we also need a bias for each neuron. We need 1 bias, 2, 3, 4, 5, 6. So we need 6 parameters for the biases. Therefore, in total, we need 26 learnable parameters for this model. And this has been proposed, this multilayer perceptron has been proposed several decades ago, but it was not successful at that time until recently. And the reason is we have to go deeper. And you may see this picture on the internet, but the father of deep learning is Professor Hinton from University of Toronto. And here is the deep neural networks that make the big surprise in a image recognition computation. And I have asked you to figure out how many model parameters in a simple multi-layer perceptron. And for this deep learning model over here, there are 60 million parameters. So this may looks complicated for you. But as I mentioned earlier, we need to have a modular view of the machine learning models. So let us look at this, which is called AlexNet. So it was a winner in the ImageNet competition 10 years ago. And that competition has 1.2 million images, and the task is to classify the images into 1,000 classes. And let us look at the AlexNet in 3 parts. The first part is the inputs. Right? So they are just the input image, which are the pixels. And we look at the last unit over here, which is basically the softmax of 1,000 classes. That is 1,000 class multi-class classification. So this softmax is basically the extension of sigmoid for multi-classes. So the model here, for this particular layer over here, actually this is a logistic regression model. And then what's in the between? The between are 5 convolutional layers with max pooling, that is here 1, 2, 3, 4, 5. These are the 5 convolutional layers with max pooling. And there are also 3 fully connected layers, as we see in our linear models. So you see here labeled as dense, so that means they are fully connected layers. We have 1, 2, and 3. So there are 3 fully connected layers. And what these things are doing is simply some kind of fancy feature extraction. And this is also called representation learning. And so if you see the word representation learning, is basically kind of fancy feature extraction. And we use many layers to extract the feature for classification into 1,000 classes. Right? So that's the input and representation learning and a classification model, basically a logistic regression. So in this way, we can understand a complex model more in an easier way. And this is also why I emphasize the concept of machine learning pipeline and designed the API in the PyQ package. So that is about computational graph. It can really help you to understand complex machine learning models. In the last section, we will look at PyTorch, a library designed for deep learning.